Inside Myanmar's Thilawawa Special Economic Zone, fabrication yards operate around the clock, producing industrial infrastructure for the global energy sector. On one particular line, a batch of 12 6-inch piping spools is ready for final dispatch. Their destination is a gas processing plant, where they will integrate directly into the main process flow. To the naked eye, the construction is flawless. The angles are precise, and the weld caps are perfectly uniform. But these spools are not carrying water. They are built to transport sour gas, highly saturated with hydrogen sulfide, pressurized to 150 bar. Before a single spool leaves the yard, a QA/QC inspector flags the batch, issuing a non-conformance report. They have identified 5 invisible errors that require the entire assembly to be scrapped. In industrial process piping, a flawless exterior means nothing. A pipe's safety is verified entirely by its adherence to ASME engineering codes and a rigid, unbroken chain of documentation. The governing standard for this system is the ASME B31.3 Process Piping Code. This specific gas stream falls under Category M, a classification reserved for highly toxic, lethal fluids, where a single fracture can be fatal to anyone within 100 meters. The first error begins with the metal itself. The engineering isometric drawing mandates ASTM A312, a high-grade stainless steel. The physical pipe sitting in the yard is stamped ASTM A106, standard carbon steel. Carbon steel is the workhorse of oil and gas piping, but it cannot survive in a wet, highly acidic hydrogen sulfide environment. When sour gas contacts the inner wall of a carbon steel pipe, the acid reacts with the iron. This reaction releases free hydrogen. The small hydrogen atom forces its way directly into the metallic lattice of the steel wall. Once trapped deep inside the metal, those isolated hydrogen atoms recombine into larger molecular hydrogen gas. They expand, generating immense localized pressure that physically pushes the steel grains apart. Microfissures erupt inside the wall. They rapidly link together, ripping a jagged path outward until the pipe ruptures. This is sulfide stress cracking. To stop this reaction, the steel requires a minimum of 10.5% chromium, the exact chemical composition of the stainless steel that was originally specified. The chromium forms a passive oxide layer that blocks the acid. Substituting standard steel for stainless steel in Category M service guarantees a structural breach. It is the installation of a timed explosive device. The investigation then moves to the joints. The carbon steel pipe has already been fused to the correct stainless steel flanges. This reveals the second fatal flaw. To join them, the welder used standard E7018 carbon steel filler wire. Fusing 2 completely different metals in the presence of an acidic fluid creates a dissimilar metal joint. It functions exactly like a battery. Electrons begin flowing rapidly from the active carbon steel directly into the noble stainless steel. As the electrons leave the carbon steel, the metal physically dissolves. This is galvanic corrosion, and it intensely attacks the weaker metal right at the weld seam. Because this system operates at 200 degrees Celsius, the heat acts as a catalyst. For every 10-degree increase, the rate of chemical decay roughly doubles. A welder can execute a structurally flawless pass, but thermodynamic incompatibility will consume the joint from the inside out. Next, the inspector examines the mechanical seal, the bolted flange connection tasked with holding back 150 bar of pressure. Here lies the third error. The fabricator saw a Class 900 flange and assumed that rating guaranteed a fixed pressure threshold, regardless of the environment. This line graph maps the ASME B16.5 standard for pressure temperature ratings. Notice the strict inverse relationship. As the temperature of the steel increases, its yield strength drops, so its pressure rating must drop with it. When we plot this system's operating temperature of 200 degrees Celsius, the maximum allowable pressure plummets down the curve. The margin of safety compresses dangerously close to the 150 bar operating limit. Pushing a system this close to its limit requires a perfect mechanical seal. Which brings us to the fourth error. The fabricator installed a standard spiral-wound gasket. High-pressure Category M systems mandate a ring-type joint, or RTJ. This seal uses a solid metal ring. When the flange bolts are torqued, the extreme downward force physically crushes the soft metal ring into a machined trapezoidal groove. The metal deforms, filling every microscopic imperfection in the steel face. It creates an impenetrable metal-to-metal barrier. A standard spiral-wound gasket cannot survive this level of mechanical stress and will blow out. The clamping force of the steel bolts means nothing if it is crushing the wrong geometric profile. The physical errors have been cataloged, but the most important question is procedural. How did the wrong pipe and the wrong filler metal get past the supply depot and onto the welding floor? The fifth and final flaw is a broken chain of traceability. The spools are missing their material test certificates. The Material Test Certificate, or MTC, proves the exact chemical composition of the steel. It links directly to a unique heat number physically stamped onto the pipe, tracing that metal back to the specific cauldron it was poured from. Because the MTC was missing, the fabricator relied entirely on visual inspection. They completely bypassed the mandatory Positive Material Identification Test, or PMI. A single inspector with a handheld XRF scanning gun could have prevented this sequence. Pressed against the metal, the gun fires X-rays into the surface, reading the atomic makeup of the pipe in seconds. It would have immediately flagged the missing chromium. In industrial engineering, if a component lacks verified documentation matching its physical chemistry, it is legally and functionally classified as a failed component. 3 spools out of 12 contained deadly material mismatches. The remaining 9 look correct, and their physical stamps claim they are stainless steel. But QA/QC rulings are binary. Because the site lost traceability control and skipped the PMI testing, no stamp can be trusted. The inspector rejects the entire batch. All 12 spools must be destroyed and refabricated. This strict zero-tolerance policy exists because the ASME B31.3 code governs every millimeter of the plant's architecture, starting at the baseline thickness of the pipe wall. The math strictly bounds the system's survival. The wall thickness must account for the fluid's design pressure, the outside diameter of the pipe, and the specific material allowable stress at extreme temperatures. When you scale those strict mathematical limits across an entire facility, the result is a dense, interlocking matrix of millions of calculated variables operating perfectly in sync. Getting this matrix right commands the majority of engineering hours on an EPC project, routinely consuming 30